Hello. This is Nicholas, and I'll just be doing a quick video on Clairaut differential equations. And those are of the form y equals xy prime plus phi of y prime. So phi is a function of solely y prime. And notice that if I have this general form, and if I differentiate it, I'm going to get y prime equals xy double prime plus just a y prime plus phi prime of y prime. And so every time you get a Clairaut equation, when you differentiate it, you can always just, I forgot a y double prime here, the derivative of the input by the chain rule. So every time you differentiate, you can cancel out a factor of the y primes, and you can get 0 is x minus, or plus, x plus phi prime of y prime times y double prime. So you can set y double prime equal to 0, and so then y prime is just a constant. Now, notice here, y is not just it's not going to be cx, or c sub 1x plus c sub 2. It's actually going to be something different, because look, see, we already have the function solved for y, and we have a y prime and we have a y prime here. So y, when we go to integrate, is actually just going to be x c, because y prime is c, plus phi of c, because again, the phi of y prime, well, y prime is c. And the other scenario is that we have x plus phi prime of y prime equal to 0, and that's pretty easy to solve. That's separable, and we could go through it pretty easy from there. I'm not going to go through the details right here. As an example, if we had y equal xy prime minus e to the y prime, we could differentiate both sides, and we get y prime equals xy double prime plus y prime minus e to the y prime times y double prime. Ooh, cool. We can cancel these out. We can get 0 is equal to xy double prime minus e to the y prime y double prime. Or in other words, 0 is equal to x minus e to the y prime times y double prime. And so y double prime is equal to 0, so y prime is equal to c. And so y here is equal to xc minus e to the c. Again, because if y prime is equal to c, in this original equation where we have this y prime, plug in a c, and this y prime, plug in a c. That's how I got that solution there for y. So don't just integrate y prime again in this specific case of the Clairaut equation. Now the other case is when x minus e to the y prime equals 0, or in other words, x equals e to the y prime, or in other words, natural log of x is equal to y prime. And that's pretty easy to solve for y. You end up getting, after some integration by parts, that y is equal to the integral of the natural log of x, which is x times the natural log of x minus x. Or in other words, x times natural log x minus 1. And so there's two solutions for y, and we have two different names for these two solutions. This first solution here is called the general solution. Why is it general? Because it's got the constants, so it is an infinite family of functions of y. And then this solution here is, and by the way, I didn't put the plus c at the end. There's no need to, for when I integrated xl and x, or for when I integrated natural log of x and I got xl and x minus x. There's no need to put a plus c at the end, because when you differentiate it, you're just going to get 0 for the constant again. when I differentiate it and I plug it in for y prime, the constant's just going to go away to 0, so you don't need the constant anyway. So this solution here, the x ln x minus x, is known as the singular solution. Why singular? Because it's only one curve. There's only one curve defined by x ln x minus x. And I'm going to take a little trip to Desmos because these the singular, they have a geometrical meaning, the singular solution and the general solution. So I'm just writing them down real quick. Okay. So now I'm going to go to Desmos here, and I'm going to do some graphing to show you. So let's first plug in x. Oh, there we go. X ln x minus x. Okay, and now that's our singular solution. Now our general solution was xc minus e to the c. I'm going to say let c be equal to 1, so I would get just x minus e. That's pretty cool because notice they're tangent to each other at exactly e. If I plug in 2 for c, I get 2x minus e squared. Look at that. They're tangent at exactly e squared, and they intersect each other. Let's say I let c be 0.5. 0.5x minus e to the 0.5, and look at that. They are tangent to the curve at exactly the square root of e, or e to the 0.5. So I kind of want to graph a little more. They're just a little cool. Let's do 4x minus e to the 4th. And that one is tangent at exactly e to the 4th. So in general, the singular solution creates a curve where the general solutions for all values of c are tangent to that singular solution. That's pretty cool, I think. And in this particular case, for the value of c, the line is tangent at the point e to the c. That should make sense based on this graph, and the way the graph looks is pretty cool. If I try another one, minus e to the and that's going to get me tangent. Oh, looks like there's a bunch of you can make a really cool shape with this. So it's tangent there somewhere. It's not giving me the exact point on Desmos. So I think that's pretty cool. How do we know they're tangent? If we do some derivative stuff, let's see. Let's say we wanted to construct a line tangent to the curve x ln x minus x at x equals e, for example. We should get the equation x minus e using the usual procedure. So we have y minus y1 is equal to m times x minus x1. So our curve y is x ln x minus x, so the derivative has to be the natural log of x, since that's what we integrated to get x ln x minus x. So now I plug in at e, so y of e is just 1, so our slope there is 1, and at the point, we're considering the point, the x coordinate 2.718, we're considering x equals e, and y then would be, if we plug in into this, this should have been y prime of e. See, now if we plug in y of e into the original function, we get e times 1 minus e, or just 0. So we have y minus 0 is equal to 1 times x minus e, or in other words, y is equal to x minus e. So it is indeed tangent. And in general, I mean, if you plug in, say, the point C, y prime of C, our slope, is e to the c. Okay. My bad. Y prime of c is the natural log of c, and y of c is c ln c minus c. So when we plug this in, we get y minus c ln c plus c, because it's minus a negative, is equal to ln c times x minus c. Y is equal, y minus c ln c plus c is equal to x ln c minus c ln c. Okay. Those will cancel out. Y is equal to x ln c minus c. And so all we've done to our constants now is just shifted them, in essence. See, this does match up with this general solution here, because you could call this c sub 1 instead, for a different constant, because we don't know if it's necessarily the same constant as here. And all we've done to go from the general solution to the particular solution is we've said, well, let's let c sub 1 be the natural log of c. Or let's let the natural, I'm sorry, I mixed that up. Let's let the natural log of c sub 1 be equal to c. Or in other words, e to the c is c sub 1. So those do match up with each other, and that would show that at least for this differential equation,